In this and the next few videos, we're going to talk about decidability and problems that are decidable. We'll also look at problems that are not decidable and begin to explore what's outside of this area. Let's begin with an overview of what decidability means. Remember that Turing machines can have several different outcomes. They can either halt and accept, they can halt and reject, or they can fail to halt, in which case we say they loop. A problem is decidable if there exists a Turing machine that will always halt and give you the right answer. So basically it means that it's computable. We can write an algorithm for solving the problem if the problem is decidable. And that algorithm will always terminate with the correct answer. So many questions are decidable. Many problems are decidable. And this is good. It means we can create a program to answer these questions. They're very much computable in that sense. In particular, every question about regular languages is decidable, pretty much. This is a very simple set, and anything you can ask about a regular expression or a regular language or a finite state automaton is decidable. We can create programs to handle these things, and our programs that deal with regular languages will terminate. When we move up the hierarchy to context-free languages, some of the questions about context-free languages are decidable, but there are some interesting questions that are not decidable. So we start to get a little bit more interesting here because some problems in this area are not decidable. When we get into the question of Turing machines, we'll find that many of the questions about Turing machines are not decidable. And it turns out that some are not even Turing recognizable. Our first example of a problem that is not decidable is called the halting problem. And this is the question of whether a Turing machine will loop or not. Or to put it in terms of programming languages, if you're given a program and asked the question, will this program terminate or not, that problem is solvable for many programs, and you can find a proof or give the answer, but in general, it's not decidable. In general, you can't always tell whether a program or an algorithm will terminate. So the halting problem is not decidable in its general form. And beyond the question of decidable, some problems may be Turing recognizable, or to put it another way, some languages may be Turing recognizable, although they are not decidable. But we'll see that some languages are not even Turing recognizable. And while everything about regular languages is decidable, and many questions about context-free languages are decidable, or at least Turing recognizable, many questions about Turing machines are not decidable, and some questions are not even Turing recognizable. What is the halting problem, again? Well, it's simply the question of determining whether a program will stop or not. Will it ever terminate for sure, or will it loop forever? And the halting problem is asking that question in general. In other words, is it possible to create an algorithm that would take any arbitrary program and answer the question, will it halt always, or will it possibly loop? We can apply the halting problem to programs that are written in some programming language, or we can apply the question to a Turing machine. So to state the halting problem this way, given a Turing machine and some particular input string, when that Turing machine is run on that input string, will it halt or not? And expressing the problem in terms of computers, the same question is, given a program written in your favorite programming language, C or Java or whatever, will it ever get into an infinite loop, or will it always terminate? With many programs, we can analyze them, and we can say for sure, yes, I can see why this program will always halt. I can prove it beyond a shadow of a doubt that this program will always halt. Or we might be able to look at some programs and say, yes, this program will always loop. It will never halt. Or perhaps we can look at the program and say, yes, sometimes it will halt on some inputs and some it won't halt on. But the problem is general. Can we come up with an algorithm that, given an arbitrary program, determine whether it will always halt or will sometimes loop? That is the halting problem. And as I said, it's undecidable. By undecidable, I mean that in general, we can't always know whether a program will halt or not. About the best we could ever do is just run the program and see whether it halts. Well, that would tell you for sure, if it halts, this idea, this algorithm of just running the program would itself halt. But on the other hand, if we just run the program to see whether it halts and it doesn't halt, how can we know? Maybe we just haven't run the program long enough. We should keep running it. But of course, this is not an algorithm because it may never terminate. So as I said, the halting problem for programs in general or for Turing machines in general is undecidable. But that doesn't mean we are at a complete loss, because for many programs, we can always prove that this program will always halt. Or for other programs, we might be able to prove that it may sometimes loop. But for programs in general, the halting problem is undecidable. Now let's look at some problems that are decidable. By decidable, we mean that we can write an algorithm that will give us the right answer and will always terminate. Or we could say it another way. If a problem is decidable, then there exists a Turing machine that, when given an instance of the problem, will always determine the answer and either accept or reject, but will never loop. Here's an example problem that is decidable. Given a deterministic finite state automaton and an input string, will the finite state machine accept that string? We know how to do that. We take our deterministic finite state machine and we put our pencil on the initial state and we move through the input, and then we move our pencil from state to state. And then when we get to the end of the input string, we ask ourselves, are we in the final state or not? So that's basically how we execute a finite state machine on a given string. And that process is simple, straightforward, and will always terminate. We'll get an answer. Yes, that deterministic finite state automaton accepts that string, or we might get the other answer, no, that deterministic finite state automaton does not accept that string. Either way, it's decidable. So we get an answer. We don't go on looping forever. So languages are decidable. Okay, so we give formally we say that a language is decidable. And here I've given you a problem, and we have to really express this problem in terms of a language. So the way we do that is pretty straightforward. We will create a language corresponding to this problem, and every instance of the problem will be a string. And the string is either in the language, in which case the answer to the problem is yes, or it is not in the language. So here the problem, an instance of the problem would mean a particular deterministic finite state automaton and a particular string. That's an instance of this general problem. And so we can encode the finite state machine and the input string into some sort of a string X. And then we run our Turing machine on it, and if our Turing machine accepts, the answer is yes. And if our Turing machine rejects, the answer to the problem, to this instance of the problem, is no. Here we see the same thing a little bit more formally. Here we're specifying a language. Okay, I'm describing a set of strings, the strings such that something or other here. Okay, and we're going to call this language A for acceptance. A stands for acceptance for deterministic finite state automata. Okay, and what is this language? The angle brackets here indicate that we're taking something that's an abstract quantity and we're encoding it into a string. So the abstract quantity we have consists of two things: B, which is a deterministic finite state automaton, and W, which is a string. Well, encoding W into a string is, trivial because W is a string. But encoding a deterministic finite state automaton into a string is a question of design, and we have to specify exactly how we're going to encode the deterministic finite state automaton into a string. But somehow, we have to list what is a deterministic finite state automaton. Well, we talked about that. It's a quintuple with states, an initial starting state, a transition function, some final states, and an alphabet. And we can encode all of those things somehow into characters or symbols or even bits. So we can encode an instance of the problem into a string. An instance of the problem consists of a particular deterministic finite state automaton and a particular string W. And once we encode that information into some sort of a representation, we can ask, is it a member of this language? And as I said, this language is decidable. We can create a Turing machine that will take such a string, which is the encoding of a deterministic finite automaton in W, and tell you yes or no that deterministic finite state automaton would accept that string or not. Now, there's some possible confusion here because we're dealing with two different languages. At one level, we're dealing with a deterministic finite state automaton, and that defines a regular language. And we're dealing with a string, which is an input to that deterministic finite automaton. So we're asking, is W a member of the language described by the deterministic finite automaton? At another level, though, we're dealing with a separate, different language, and that language we're calling A sub DFA. And the strings that we're asking about are much more complex. This language is much more complex. It's not a regular language. It's not a context-free language. But we can say it is a decidable language. And the strings that are members of this language look like this: an encoding of a deterministic finite automaton plus a string such that the deterministic finite automaton accepts that string. Okay, I've said several times that this language is decidable, but what we need now is a proof that it's decidable. And in order to prove that a language is decidable, what do we need to provide? Well, we need to provide a Turing machine that decides it. In other words, a Turing machine that always halts and tells you yes or no, this particular deterministic finite state automaton accepts the string or not. Or to say it another way, we need to provide an algorithm for determining whether this is a string in the language. So we need to provide a Turing machine that will be given as input the encoding of two things: a deterministic finite machine and a string. Now there's some questions about how we're going to encode the deterministic finite state automaton, but we won't go into those details. We just assume that we can encode the finite state machine because we can encode anything in zeros and ones. So our Turing machine is going to have two separate parts. The first part is going to be a check to make sure that B is a valid representation of a deterministic finite state machine. We can provide our Turing machine with any conceivable string, and it has to recognize whether it's a member of A sub DFA. And in order to be a member, B has to be a deterministic finite state automaton, and B has to accept W. So the first thing we have to check is to make sure B is a valid representation of a deterministic finite state automaton. If it's not, we can reject immediately. But if it is a valid representation, then the next thing our Turing machine does is to simulate that machine on W. And we know how to simulate finite state machines. We've described how they work quite precisely. And given a string, we will go through the string, and in linear time, based on the length of the string, we will determine whether that string is accepted or not by that finite state machine. If our deterministic finite state machine reaches a final state at the end of W, then B accepts W, and so our Turing machine needs to accept its input. Otherwise, if B doesn't reach a final state by the time W is exhausted, then our Turing machine must reject. And I've described this algorithm pretty much in outline, and I've glossed over the details of how we're going to represent deterministic finite state machines in string form. But you can still see that the algorithm is there, and it's always going to halt. And we could go into more detail and maybe prove, give an argument for why it'll always halt. But you've worked with deterministic finite state machines and seen how they operate, and so you know that this algorithm for checking a string by a deterministic finite state machine is simple and will always halt. So we don't need to I don't think we need to go any further to prove that this Turing machine will always halt. It is self-evident, and therefore, since the Turing machine always halts, this language, the language that we're looking at, is decidable. Let's keep going with some questions about regular languages. Let's look at non-deterministic finite state automata here. Previously we were looking at deterministic finite state automata, and now we want to consider the question of whether a non-deterministic finite state automaton accepts a given string. So this is a similar language to what we had before. There's an N here instead of a D this time, so we're talking about non-determinism. Before we were talking about the acceptance problem for deterministic finite state automata, but here we're talking about the acceptance problem for non-deterministic finite state automata. And this time, the language consists of those strings such that B is an encoding of a non-deterministic finite state machine and W. And if that machine accepts that string, then it's a member. Then this encoding is a member of the language. Just like before, to prove that this language is decidable, we need to provide or construct a Turing machine that takes an arbitrary string and determines whether that non-deterministic finite state machine accepts the candidate string, W. So our input is a representation of a non-deterministic finite state automaton and a string W. And so we have to build a Turing machine that takes a string and determines, is it a valid representation of a non-deterministic finite state machine? And if run on W, would that finite state machine accept W? Well, there are two approaches that we could take in building that Turing machine. Both are valid. One might be easier than the other. It's not clear which is easier, which is more straightforward, but let's talk about both. In the first approach, all we do in our algorithm that we're providing as part of the proof is to simulate the non-deterministic finite state machine on the string W. Now the simulation can be a little bit complicated. Remember when we talked about non-deterministic finite state machines, I said we simulate it by moving through the input one symbol at a time, and at each step of the input we move from one transition to another, except since this is a non-deterministic machine, at any one time we can be in several states at once. So I said, imagine putting one finger on each state you're in, and I'm assuming you've got enough fingers because we could be in several different states. And if you get the next symbol from the input, say it's some arbitrary symbol like a C, we look at all the states that we're currently in and whether there are any transitions out of those states labeled with that same symbol C. And if so, we move that particular finger to a new next state. And if there are no transitions, we have to remove the finger altogether. So in that way, we move from one set of states to the next set of states. And on reaching the end of the string, we ask, is any one of our fingers on a final state? And if the answer is yes, then we must accept W. So that's the first approach to building a Turing machine that checks whether this string is a part of the language. The second approach is a little bit different. Here what we do is we convert the non-deterministic finite state automaton to a deterministic finite state automaton. We discussed the process of converting a non-deterministic machine into a deterministic machine earlier in a previous video, and it's rather complicated. Remember, with the epsilon closures and so on, but the algorithm was an algorithm, meaning it was decidable, it was computable, it will terminate. Okay, there is an algorithm to do it, and we sketched out the algorithm, but in theory you could write a Turing machine to do it. It would take a lot of states, but of course you could do it. So that part of the solution is decidable. There is an algorithm that will terminate to convert a non-deterministic machine to a deterministic machine. Then, once we have the deterministic machine, well, we just create a Turing machine, a second Turing machine, to check to see whether it accepts W. And we just did that for the acceptance language for deterministic finite state machines. So we know that Turing machine exists. And then we've got these two Turing machines. We need to glue them together into a larger Turing machine that works in two steps. First, it converts the non-deterministic to a deterministic machine. Then it runs the deterministic machine on the input string. And if that simulation accepts, then we accept. Otherwise, if that simulation rejects, then we reject. So either way, we've shown that we can build a Turing machine that will take an arbitrary string. First, it checks to make sure B is the representation, a valid representation of a non-deterministic finite state machine, and that our string has the proper form, if you will. And second, it checks to see whether that non-deterministic finite state machine will accept the string W. And if so, it accepts, and if not, it rejects. So this language is decidable. In talking about regular languages, we saw there was an equivalence between deterministic finite state automata, non-deterministic finite state automata, and regular expressions. And so, as the third fork of this, we can ask, if we are given a regular expression and a string, can we decide whether that regular expression generates that string? Is that string described by the regular expression? And we can formulate this problem also as a language, and here we're calling it the acceptance problem for regular expressions. So given a regular expression R and a string, does that regular expression describe that string? Can it generate that string? And we already know that we can write an algorithm to do this, so the answer is yes, this language is decidable. We can build a Turing machine, or if you want to say it another way, we can write a program that, given a regular expression and a string, it will determine whether that regular expression generates that string. or whether that string is described by that regular expression, if you want to say it that way. Or it will determine whether the representation of the regular expression in the string is in the language. So, since that algorithm will always halt, it's a pretty straightforward computable algorithm, and we could program it up in a way that it always halts, then this language is decidable, or to say it another way, the problem itself is decidable. I am not going to talk too much about termination here because the algorithm is straightforward, and that's the kind of thing you really talk about in compiler class. These algorithms are not only guaranteed to terminate, but they can be extremely fast too. So oftentimes the question of whether an algorithm halts or not is self-evident. Okay, we don't need to prove it because it's so obvious. On the other hand, with some algorithms, it's maybe not so obvious, and we really ought to prove it more carefully. Again, I want to say this and make it really clear. Many programs can be proven to always halt. We can look at an algorithm and we can analyze it. We can say, well, this loop can only go so many times before it has to terminate. Or some other kinds of reasoning like that. That's the issue of program verification. Program verification involves two things. It involves proving that the program gives the right answer, and it involves proving that the program always halts. So in proving that a program is correct, you really need to prove those two things, that it gives the correct answer and that it always gives an answer. It doesn't ever infinite loop. And many programs can be proven to always halt and to give the correct answer, and we can do a formal proof if we feel we need to. But again, the halting problem itself is not decidable. The fact that we can prove it for some programs does not mean that the halting problem is decidable. In general, we cannot come up with an algorithm that will always be able to tell whether a particular program halts or not. Before we finish with this video, I want to talk a little bit more about the algorithm for determining that a string is in this language, for deciding the language of acceptance for a particular regular expression. So given some string representing a regular expression and a potential input w to that regular expression, the algorithm that I want to suggest we use involves an algorithm that we learned about in a previous video. Remember, we saw how we could convert any regular expression into a non-deterministic finite state automaton. Here I'm going to call that non-deterministic finite state automaton B prime because we used B in the previous slides. So given any regular expression, we can break it down into pieces. If you will, we can parse it. So at the outermost level, a regular expression is made up of either union or concatenation or star, and the smaller regular expressions like x and y are themselves representable with non-deterministic finite state machines. So if we can figure out the non-deterministic finite state machine for x, shown in black here, and the non-deterministic machine for y, shown in black here, we can figure out the non-deterministic machine for their union as follows. We add a few more states and we add a few epsilon edges. It looks something like this. And likewise for concatenation, we could show how we can concatenate two regular expressions, or more precisely how we can build a non-deterministic finite state automaton out of the non-deterministic finite state automata for the pieces, x and y. And then for star, there was also a way to build the non-deterministic finite state automaton, given that you know the non-deterministic finite state automaton for the sub-expression x. I can't remember the exact details, but it was something like this. And so we have an algorithm that will convert a regular expression into a non-deterministic finite state automaton, call it B prime. Once we get that, we can then construct a string, which is the representation of this non-deterministic finite state automaton, and again our input string. And then we can use the Turing machine from the last theorem to decide whether this new string with B prime and W is accepted by the non-deterministic finite state automaton. Is W accepted by the non-deterministic finite state automaton B prime? So we can take this string and use the Turing machine from the last theorem, which we know is a decider, to decide this. So showing this algorithm is important because it shows how we can build up algorithms from previous algorithms. Or to put it another way, we can build up Turing machines from smaller Turing machines that we already know how to build. So if we're trying to build a decider for some particular language, we can construct that Turing machine out of Turing machines for pieces of the problem that are deciders for those pieces. So you can view this acceptance problem here for non-deterministic finite state automata as a smaller problem, or a problem we've already solved, for which we already have a decider. We have an algorithm that will decide it. So this is very familiar to programmers. You build new algorithms out of older algorithms that you've already developed. Okay, and if those algorithms that you're using are deciders in the sense that they always halt, then you're safe. So you can always use a program as long as you already know it halts in building a new, larger program that you want to show always halts.